Hello, welcome to another module in this massive open online course. So, we are looking at amplitude modulation, alright, and we have said an amplitude modulated signal is where the amplitude of a carrier, right, a carrier says cosine 2 pi fct at carrier frequency fc is modulated by the message signal mt. Alright. So, today and we have looked at various concepts such as modulation, right, modulation index, over modulation, etc. So, today let us look at the spectrum of an amplitude modulated signal. Okay. So, let us look at the spectrum of an AM signal. The spectrum of an AM or amplitude modulated signal, and our consider a message signal. So, consider a message signal MT with spectrum MF. Correct. So, let us draw a typical spectrum MF. So, let us say this is our spectrum. Okay, so let us say this is minus FM, this is FM, where FM equals the maximum frequency of MT, correct, and this is our spectrum MF. Okay. So, this is the message spectrum MF. So, we have MT with spectrum MF, this MT is our message signal, correct. MF is the message spectrum. Okay. And now, our amplitude modulated signal, remember xt equals AC 1 plus Ka MT into cosine 2 pi fct. This fc is cosine 2 pi fct is the carrier, or A cosine 2 pi AC cosine 2 pi fct is the carrier. Remember, Ka is the sensitivity, this Fc is the carrier frequency. Okay. So, we have our amplitude modulated signal which is given as AC times 1 plus Ka MT into cosine 2 pi fct. This can be expanded as AC into cosine 2 pi fct plus, correct, AC Ka MT cosine 2 pi fct. Now, let us look at the spectra of these two components. Now, consider cosine 2 pi fct. I can write this as e to the power of j 2 pi f c t plus e to the power of minus j 2 pi f c t divided by 2, correct. Cosine 2 pi f c t is e to the power of j 2 pi f c t plus e to the power of minus j 2 pi f c t divided by 2. And the Fourier transform of the exponential of the complex exponential is given by the impulse, that is e to the power of j 2 pi f c t has Fourier transform, this has Fourier transform delta f minus f c, e to the power of minus j 2 pi f c t has Fourier transform delta f plus f c. Therefore, cosine 2 pi f c t, this has the Fourier transform which is half Fourier transform of e to the power of j 2 pi f c t, that is delta f minus f c plus delta f plus f c. And therefore, A c, if I multiply this by A c, that is A c cosine 2 pi f c t, this has the Fourier transform A c cosine 2 pi f c t has the Fourier transform A c by 2 delta f minus f c plus A c by 2 delta f plus f c, and therefore, if you draw the spectra of this part, that is the carrier, it comprises of two impulses A c by 2 at f c and another impulse scaled by A c by 2 at minus f c, correct. So, this is the Fourier transform or f t of A c this is the frequency axis, okay. This is the Fourier transform of A c cosine 2 pi f c t, that is it has an impulse of scaled by A c by 2 at f c, impulse scaled by A c by 2 at minus f c, which can be expressed as A c over 2 delta f minus f c plus delta f plus f c. Okay. So, that is the spectrum of the first component, that is a carrier component. Okay. So, we are calling this as the A c, this is the pure carrier. Okay. This is the pure carrier. Now, let us look at the other component, that is A c k a. So, observe A c k a m t times cosine 2 pi f c t Now, this is a multiplication in the time domain Now, the Fourier transform of A c of this part will be A c k m f. Fourier transform of this part will be half delta f minus f c plus delta f plus f c. Fourier transform of cosine 2 pi f c t is half delta f minus f c plus delta f plus f c, plus the two signals are multiplied in the time domain, which means the respective spectra will be convolved in the frequency domain, all right. So, A c k m f will be convolved, that is multiplication in time domain becomes the convolution this becomes the convolution in the frequency domain. Therefore, this is now I can write it as two separate convolutions AC Ka AC K over 2 MF convolved with delta F minus FC plus AC Ka by 2 MF convolved with delta F minus Fc. Now, MF convolved with the delta F minus Fc simply shifts the spectrum MF to Fc, that is if the if MF, that is MF convolved with delta F minus Fc shifts the spectrum to Fc, MF convolved with delta F plus Fc shifts the spectrum to minus Fc. So, this from the properties of the delta function you can check that this is simply shifts MF to Fc and this is plus Fc delta F plus Fc, this shifts MF to minus Fc, and further we have the scaling by this ACK by 2, this is simply a ACK by 2 is simply a scaling factor. So, what we are going to have net is basically now we are going to have the spectrum which looks as follows. We are going to have at Fc we are going to have MF minus, so this is basically your MF shifted to Fc, that is M of F minus Fc half AC Ka, that is this is basically your shifted to Fc correct. Correspondingly over here we are going to have the image that is shifted to minus Fc. Okay, so, this is half AC, this component is half AC KAMF plus Fc plus if I add the spectra of the carrier, now I am going to have two impulses. So, this is your impulse AC by 2, the AC by 2 AC by 2 delta F, I believe delta F minus Fc, this is your impulse and this is your impulse AC by 2 delta F by Fc. So, this corresponds to the carrier, we have added the, so these two impulses correspond to the carrier wave, these two correspond to these two triangular bands correspond to the bands of the spectra of the original message shifted to Fc, shifted to minus Fc, and this is the complete spectrum of the AM signal, that is the message spectrum, that is a shifted message spectrum plus the carrier component. Okay. So, this is the your complete, that is your spectrum of the AM signal. So, this is your spectrum of the AM signal. this is the spectrum of the AM signal, okay, or the amplitude modulated signal, which is given as, remember the AM signal which is given as 1 plus KMT AC cosine 2 pi FCT. This is the spectrum. All right, look at this. This is symmetric about the origin. Correct. It contains two bands, one shifted on the positive frequency side, one on the negative frequency side. Correct. One corresponding to the MF shifted to FC, MF shifted to minus FC. Correct. Now, these two over here, these two bands over here, these two over here, that is minus FC. If I look at this, this is minus FC plus FM, this is minus FC minus FM, this is FC plus FM, FC. These two bands between FC to FC, FC minus FM to FC and minus FC to minus FC plus FM, these two bands are known as the lower side band. Or the LSB. Let me just write this a little clearly. These two bands comprise the lower side band or LSB, and these two bands, if you look at the bands between minus FC minus FM to minus FC, that is the one being shaded in orange, and FC to FC, FC to FC plus FM, that is if you look at these two, if you look at between F minus FC minus FM to minus FC and FC to FC plus FM, if you look at these two bands are known as the comprise the upper side band or the USB. That is the outer side bands, that if you look at the outer side bands of this modulated AM signal, they comprise the upper side band. The inner side bands of this AM modulated signal comprise the lower side band, and these are going to play an important role later on when we talk about single sideband modulated signal. That is when we are going to transmit only one of the sidebands, either the upper sideband or the lower sideband. That is a different modulation technique which is known as single sideband modulation, and that has an important role in communication because it results in a savings of bandwidth. Correct? Alright. So, this is basically the complete spectrum of the AM signal, which we can see comprises of the carrier wave component, which is represented by the two impulses at minus FC and FC, and also the two shifted versions of MF, that is MF minus FC at FC and MF plus FC at minus FC, alright, and these are appropriately scaled. The impulses are scaled by AC by 2 and the spectra, that is the shifted bands of the message, are scaled by half AA, half AC KA. Okay. So, this is the complete spectrum, of the AM signal, and in future we will examine and we have also noted the upper side band of this message spectrum and the lower side band, and in future we are going to examine or we are going to explore single sideband modulation, that is where we transmit only the upper side band or the lower side band. So, let me also make a note of that, that is that is we have single sideband modulation which transmits only the either the USB that is the upper sideband or the LSB of the signal, that is the lower sideband. Okay, we will explore these different modulation techniques in the future where we transmit only the upper sideband or the lower sideband. Okay. Now, let us look at detection for this AM signal or amplitude modulated signal, and one of the most popular schemes for detection is what is known as envelope detection. And as the name implies, envelope detection detects the envelope, correct. This detects the envelope, this detects the envelope of the transmitted signal to recover the message. This detects the envelope of the transmitted signal to recover the message, correct. And therefore, by default it implies that if I have to detect the envelope, then there should be no distortion in the envelope. Therefore, this works only when there is no distortion in the envelope, which means the modulation index mu must be less than or equal to 1. Alright, that is the condition that we have seen before. If you go way back, if you go to our previous, if you go to the previous module, what we have seen is that for no distortion, that is the modulation index mu must be less than or equal to 1, correct. The modulation index mu must be less than or equal to 1 for no distortion. Okay. So, this is what we have seen in the previous module, alright. So, for this it takes the envelope. So, for this there should be no distortion, works only when there is no distortion of envelope. This implies mu has to be less than or equal to 1, where mu, remember mu is the modulation index. Okay. And what is envelope detection? Envelope detection employs a simple circuit which is known as the envelope detector, and that can be explained as follows. I have an input here, alright, and this is my source resistance Rs. I have a diode, correct, a capacitor which charges and discharges, and a load resistance RL, and I measure the voltage V naught across the capacitor, correct. So, now this is known as this circuit, and the AM wave is given as input the AM wave is given as input to this circuit, all right. This circuit is known as an envelope detector or a peak detector. This circuit is known as envelope detector or peak detector. As you can see, it is a simple it's a simple circuit, correct. This envelope detector, it is a very simple circuit which consists of a diode, all right, and a capacitor in parallel with resistance, that is a load resistance RL, all right, and the capacitor charges and discharges, and this tracks basically, and we are going to show how this tracks basically the envelope of the incoming signal. And as we already seen, the incoming signal or the AM wave, the amplitude modulated signal, is fed as input to this envelope detector, all right. And this circuit, we can see this tracks the peaks of the carrier or the envelope. This tracks remember the waveform formed by the peaks of the carrier, that is nothing but the envelope of the signal, all right. And how is this achieved? Let us look at this, let us look at how this is achieved. Let us draw again a simple AM modulated signal, and remember also we are considering that the modulation index is less than 1, therefore, there are no, now this is the carrier, this is an approximate so this is your envelope, correct. The actual original envelope, which is basically your 1 plus K times MT into AC, this is the actual envelope. Now, this is the modulated carrier, correct. This signal over here, this is your modulated carrier, which is fed as your input. So, this is the input V in, which is basically your modulated carrier. Now, let us say the output voltage starts from 0. Now, when the input voltage is greater than the output voltage, the capacitor charges to the input voltage, and once it reaches the peak, correct, because the diode becomes reverse biased, all right, the capacitor is cut off and it starts discharging, until again V in becomes greater than V out, at which point it starts charging, and again once it reaches the peak, the diode becomes reverse biased. As V in starts falling, the diode becomes reverse biased. So, the capacitor charges and discharges, and as you can see, it traces a path that is somewhat close to the actual envelope. So, let me draw it with a different color. So, the capacitor charges, and at this point V in starts to decrease, that is V out is greater than V in. So, the diode is reverse bias, the capacitor starts to discharge, again capacitor charges and capacitor discharges. And you can see this is the, so this is the output, this is the output VO, which is close to the actual envelope. So, VO is the output which is basically output of the envelope detector. VO is the output of the envelope detector, and you can see it is fairly close to the envelope of the input signal, that is the envelope of the incoming amplitude modulated wave. And it works on the following principle, that is when the input voltage is greater than the output voltage, the capacitor charges. So, the capacitor rises to the peak. Once the capacitor voltage reaches the peak of the carrier at that point, alright, and Vin starts to fall, the capacitor, then the diode becomes reverse biased. So, the capacitor is cut off and the capacitor starts to discharge from the load resistance R. So, basically it reaches the peak and discharges slowly until the next time instant when V in again becomes more than VO, at which point at the output voltage, the capacitor again charges to the peak, and this process keeps continuing, whereby the capacitor keeps charging to the peak and discharges slowly, thereby approximately traces the wave that corresponding to the peaks of the incoming carrier wave, and that is basically nothing but the envelope of the incoming amplitude modulated signal. So, the envelope detector works on the principle, basically the principle of envelope detector is when your AM wave, that is equal to V in, is less than VO, this implies diode equals, or when V in is less than VO, or when V in is greater than VO, the input voltage is greater than or equal to VO, diode is forward biased. So, this is your diode, let us denote this, this is basically, this is your diode D. So, V in greater than VO implies D is forward biased, and V in less than VO implies D is reverse biased. So, when V in greater than equal to VO, the diode is forward biased, okay. The diode, this implies that the diode is forward biased, correct. This implies your capacitor charges. Okay. On the other hand, when V in less than VO, correct, this implies diode is reverse biased, this implies capacitor is cut off and basically capacitor discharges. Capacitor discharges to RL. Capacitor discharges through the resistance RL. Capacitor discharges through resistance R. So, when the diode is forward biased, capacitor charges and capacitor charges to the peak of the carrier, and capacitor discharges, and remember it does not discharge very fast, the capacitor discharges slowly, if I might add, capacitor the key here is to realize that the capacitor discharges slowly, because if the capacitor discharges very fast, then it reaches the peak, that is almost going to fall down immediately, correct. So, we want the capacitor to charge to the peak and then hold to the peak and fall discharge very slowly, so that it can again charge to the peak at the next time and thereby trace the envelope rather than trace the carrier. We would like the capacitor to charge to the peak and then hold to the peak, discharging slowly, so that it is only tracking the message signal, but not discharging again with the carrier, alright. So, we want the capacitor to discharge slowly. So, in fact, the time constant of this circuit, that is the time constant of the capacitor, that is the discharge circuit, that is C into RL, that is tau, which is C times RL. This time constant has to be chosen appropriately, so that, alright, so that the capacitor does not discharge too fast or the capacitor does not discharge too slowly, alright. So, we will see, right, we will see that the capacitor, that is the time constant tau, has to be chosen appropriately, so that the rate of discharge of this capacitor has to be appropriate, so that it tracks the envelope of the incoming amplitude modulated signal. And we can see that once that happens, the output voltage of the across the capacitor is basically a close replica of the envelope of the incoming amplitude model, incoming AM signal, which is basically proportional to the message signal, because remember, the envelope of the amplitude modulated signal, if there is no envelope distortion, is basically proportional to the message signal. It is in fact AC times 1 plus KMT. So, that is how basically this simple envelope detector, which comprises of a diode and a capacitor and a load resistance, is able to recover, alright, able to recover the envelope of the incoming amplitude modulated signal, and from this the message signal MT can be recovered, alright. And the advantage of this circuit, the advantage of envelope detector is it is a simple circuit. It comprises only of a diode, a capacitor and a resistor. So, it is a very low complexity and it is a very low cost or a low budget circuit, and therefore, it makes implementation of an AM of the receiver or an AM receiver makes implementation of an AM receiver very low cost and very simple, and therefore, it is very, the envelope detector, although is not optimal, although does not yield exact recovery, as we can see, the envelope is a close approximation of the envelope of the incoming signal, but not an exact replica of the envelope of the incoming signal. Therefore, even though the approximation is coarse, the envelope detector is one of the most, envelope detection is one of the most popular schemes for demodulation of or detection of AM signals, correct, detection of AM signals, because envelope detector is a very low cost, is a very simple low cost circuit, which makes the receiver implementation, that is which makes the AM demodulator implementation, the AM detector implementation very simple and low. It enables low cost, it enables implementation of low cost receivers, which is especially suitable for broadcast applications, for instance applications such as TV transmission, radio transmission, where the broadcast equipment can be very high cost, but the receivers such as the televisions or the radios have to be very low cost. That is the advantage, it helps build receivers with very low cost because of the low complexity of the circuitry. So, this is envelope detector. To add the envelope detector, comprises only of a diode, a capacitor and resistance, correct, and therefore, it is a simple circuit suited, it is very simple circuit and it has a low complexity and low cost. More importantly, it has a low complexity and therefore, this is suited for development of low cost receivers such as televisions or radio sets in especially broadcast applications, example being your TVs or transistor sets or radio sets, etc. So, it is the attractive feature of the envelope detector is the simplicity or the low complexity of the circuit, which enables low cost implementation and therefore helps build receivers with very low cost and suited for broadcast applications. So, in this module we have seen a couple of things. We have seen the spectrum of the amplitude modulated signal, all right, seen the various components, the upper sideband and the lower sideband of this amplitude modulated signal, and we have also seen a simple technique for detection or simple technique for detection of the envelope or simple technique for demodulation of the AM signal, all right, that is the envelope detection, and we have seen the circuit and we have seen how this circuit works to yield a replica or to yield a close approximation of the envelope of the incoming amplitude modulated signal, all right. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.